Welcome, this is Professor Ridge and today's lesson 3.3, Rates of Change and Behaviors of Graphs. Today's first learning objective, find the average rate of change of a function. Finding the average rate of change of a function. So I'd just like to point out the different types of notation when we talk about average rate of change. We can do it as the change in the output value divided by the change of the input value. Sometimes you hear people say, because we can think of it as slope too. I like you to think slope, right? So change of output over change of input. Delta y, stands for the change in y, so you can say delta y or change in y divided by change of x. If you want to find the change in y, you're subtracting the y coordinates. So if you think of 2 points, right, this is the slope formula, y2 minus y1 over x2, and these are subscripts, y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. And then if we use function notation instead of the y sub 2, remember f of x is a y value. So this is the y value for the given input value x sub 2. Okay, so this is the y if this is x sub 2. So if you have the 2 points, you're going to do the slope formula. Okay, so all these pretty much the same thing, and we call this average rate of change. Right, so the average rate of change between two input values is the total change of the function values, the output values, divided by the change in the input values. So here we're defining it using it delta y over delta x, or again you can read this as change of y over change of x, and you're going to subtract the y values over subtract the x values, and then you divide those two numbers. Or if you want to leave it as a fraction, that's typically what we do, but then reduce it. Example 1, computing an average rate of change. Using the data in table 1, which I have above here, find the average rate of change of the price of gasoline between 2007 and 2009. Okay, so let's see. Gasoline costs have experienced some wild fluctuations over the last several decades. Table 1, list the average costs in dollars of a gallon of gas for the years 2005 to 2012. The gasoline can be considered as a function of the year. So C of Y, that's the cost in dollars of a gallon of gas for 2005. Okay, so if the input's 2005, the output would be 2.31. Right, so we want to find the rate of change, the average rate of change between 2007. So this will be our x sub 1, f of x sub 1, or actually be c. Okay, I'm changing my variables to x and f of x. Okay, and then 2009. So this would be my x sub 2, f of x sub 2. Okay, so my slope is going to be the change average rate of change is equal to the delta y over delta x, which is, we're going to do f of x sub 2 minus f of x sub 1. You can use y sub 2, y sub 1 also, either way, over x sub 2 minus x sub 1. All right, and so I labeled this will be my x, this will be my y. Even though this says y and c of y, then I know that can be confusing. Anyway, so we're going to do the output values, subtract them. So we do 2.41 minus 2.84 Now the order doesn't matter as long as you're consistent. You can do you can do f of x sub 1 minus f of x sub 2 as long as you switch it on the bottom as well. You got to switch both of them. So x sub 1 minus x sub 2. Okay? So if we're calling this point 2, we're going to do 2.41 minus 2.84, and then on the bottom we're going to do 2009 minus 2007. And so that will get us, let's see, 40, this will be negative 0.43 divided by 2, and then punch this in your calculator and you get negative, okay, they rounded it to the nearest cent, so it's negative 0.215, but then rounded to the nearest cent. We're going to put the dollar symbol, 0.215, but then round it to 22 cents per year. All right, so that's your answer, 22 cents per year. It's our dropping, negative 22 cents per year. Okay, so let's see here. Example 2, computing average rate of change from a graph. So remember, average rate of change, you can think slope. It's technically slope. Right? Given the function g of x, or g of t, sorry, shown in this figure 1, find the average rate of change on the interval from -1 to 2. Now this is what confuses a lot of students. This interval, remember, this is on the x-axis. This is your input values. So we're going from -1 to 2. So we're looking at this interval. So we're going to go up from -1 and see it hits the graph here, and that's going to be my first point for so the x and y. So my x sub 1, and then this is g. Actually, the input's t, so technically I should use t sub 1. And if I'm using function notation, this would be, this function's g, t sub 1. So for that first point, if it's -1 for the x or the t value, and then y value is going to be, the y value here is 4. Okay, and then we're going to go to 2, so you go up, here's 2, and then what's the x and y coordinate for that one? So again, that's going to be my point 2, but again, it's not x, it's t, so that's t sub 2, and then g of t sub 2. And then that point is, let's see, x is 2, y is 1. So 2, 1. Now basically we're going to find the slope, average rate of change. Again, think slope. We're going to do change of y over change of x, or in this case, change of g of t. So I'm going to do g of t sub 2 minus g of t sub 1 over t sub 2 minus t sub 1. Okay, and then that's going to get me, let's see, I'm going to do 1 minus 4, so the y values, I think y values, but so 1 minus 4 over 2 minus a minus 1. Okay, and normally I would just write plus 1, but for your notes. 1 minus 4 is negative 3. 2 minus a minus 1 is 2 plus 1, which becomes 3. And then negative 3 divided by negative 3 is negative 1. And the units, did they give us any units? They didn't tell us any units, so it's just the average rate of change is negative 1 unit. 1 unit per whatever the G of t stands for. Example 3, computing average rate of change from a table. After picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from home over time. The values are shown in table 2, which I have right here. Find her average speed over the first 6 hours. Okay, so we want to find the average speed. Speed is a rate of change. So we're going to do delta y over delta x. Now the y's, remember this is your output value, so that's the d of t. So we're going to do d of t. Now we're actually going to use over the first 6 hours, so we're going to use this one and this one. So let's call this t, well, whatever, it doesn't matter. So t, we'll call this our T2 and this T1, and then this is our D of T sub 2, and this will be our D of T sub 1. Okay, so D sub 2 minus D T sub 1. I was going to put 6 and 0 for the subscripts just to kind of, you know, sometimes you do it that way. It makes it more obvious of what you're doing. But anyway, these are just arbitrary, what we're calling it, 0.1, 0.2. So we're doing the subscripts 1 and 2. But I could also call this t sub 6 to kind of indicate the 6 seconds. So either way, it's up to you. Okay, so now let's plug in the numbers. So I'm going to subtract 292 minus 10 over 6 minus 0. So then we get 282 divided by 6. Punch that in our calculator. We get 47. Now notice the units. So the top is, we're going to do the D of t is on top. So this is going to be miles per, and then hours is on bottom. So that's how you get the MPH. You can write it like I did up here, miles per hour, or you can write MPH. Right? So either way. Math people tend to like this one up here, but this is the common way we write the unit, MPH. All right, computing average rate of change for a function expressed as a formula. So we have this formula, f of x equals x squared minus 1 over x. And we want to compute the average rate of change on the interval from 2 to 4. So just like we did with the graph one, remember this interval, these are our x values. This would be x sub 1, and this would be x sub 2. So we have to find the y values for each of these x values. So we don't have the graph that we can look at, but what we do is we have the formula to figure out the y value given an x value. So our average rate of change is going to be equal to, we got the change of y over change of x. The change of y, the output values, we're going to do f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Okay, so in scratch work we can figure out f of x sub 1, which is 2, so 2 squared minus 1 over 2, so that's going to be 4 minus 1 half, which is 3.5. We can write it as a decimal, or we can write it as 7 halves as a fraction. So either way. So if you didn't know what it did, right? 4, you have 4 over 1. You want to get 2 as your common denominator. So that's 8 over 2 minus the 1 half. See, now you have common denominators. So 8 minus 1 is 7. All right. Then we got to, so again, this is kind of scratch work. Now we got to do f of x sub 2. Well, x sub 2 is 4, which is 4 squared minus 1 over 4. So that's 16 minus 1/4. So 16, we want fourths. So that's 64 fourths minus 1/4 is 63 fourths. Okay, so now we got our 2 points. So f sub 2 is the 63 fourths minus f of x sub 1 is the 7 halves over x sub 2 is 4, x sub 1 is 2, and then we get, okay, so we got to punch this in our, we want to get common denominators again, so here's some more scratch work. 7 over 2, I want 4, so that's 14 over 4, so I'm going to do 63 minus 14, and then I have the common denominator 4. So that would be what, 49 over 4 over, and then 4 minus 2 is 2. And then the way you divide two fractions is you think of this as a divided by sign. And the way you divide two fractions is you multiply by the reciprocal. So 49 over 4 times 1 over 2, which gets me 49 over 8. So there's some review of fractions if you forgot how to do it. The other thing is, just learn how to use your calculator that has a fraction button. Save you a lot of headache. But that's good practice. Example 5. Example 5. Finding the average rate of change of a force. The electrostatic force F, measured in newtons, between two charged particles can be related to the distance between the particles d in centimeters by the formula F of d is equal to 2 divided by d squared. Find the average rate of change of force if the distance between the two particles is increased from 2 to 6 units. 6 centimeters, 2 to 6 centimeters. So those are our x values, or input values. So this would be like my x1, x sub 1, and this would be my x sub 2. And then just like the previous one, we got to figure out what y sub 1 and y sub 2 are. So you plug in the 2 into the formula. So f of 2, that's going to be 2 over 2 squared, which is 2 over 4, which reduces to 1/2. And then when I put in 6, we get 2 over 6 squared. 6 squared is 36. And then 2 over 36 reduces to 1 over 18. Okay, so then we got our two y values for our two input values. So our average rate of change of force is equal to change of y over change of x, which in this case would be the output values are f of d2 minus f of d1, although I used x and y. It's okay. Over d2 minus d1. So f of d2, so remember this is it's 6 and 1/18. So the output value is 1 over 18 minus, so we're going to do 1 over 18 minus 1/2. That's our output values. And then the input value is 6 minus 2. Okay, we want to get common denominators. So I got to multiply this by 9 over 9, so that's 9/18. 1 minus 9 is negative 8 over 18. Over 6 minus 2 is 4. And I'm going to flip this over. Here, let me write it over here. So I got negative 8 over 18 times. Now flip this bottom one over. 1 over 4. And I can reduce this. Let's see, I can take 2 out of this one. 4 divided by 8 is 2. 4 divided by 4 is 1. So then I get negative 2. Oh, and then I can reduce 2 and 18. 2 divided by 2 is 1. 18 divided by 2 is 9. So I get negative 1/9. And what were the units? Distance is centimeters. And did it say what the other one was? Okay. Force is in newtons. So it's newtons per centimeter. Okay, so the output value F is newtons and the input value D is in centimeters. So we got change of Y over change of X, or change of the output over the change of the input. So it'll be newtons per centimeters. Newtons per centimeter. Example 6, finding the average rate of change as an expression. Find the average rate of change of g of t is equal to t squared plus 3t but plus 1 on the interval from 0 to a. So we're saying we're starting at 0, but we're saying some arbitrary, well, in this case be t. I was going to say x, but the input's t. So some number, but we just some arbitrary number. Okay, the answer will be an expression involving a in simplest form. So basically, you're going to say, all right, this will be my x sub 1, and this will be my x sub 2. Or again, the input's t, so technically it's t sub 1, t sub 2. So if I want to do f, I should have wrote this from the other. Oh, it's not f, it's g. So that would be 0.1, and 0.2 would be t sub 2, g of t sub 2. And then, so t sub 1 is 0, and then we got to figure out g of 0. So if we put in 0, scratch work, g of 0 is 0 squared plus 3 times 0 plus 1. 0 plus 0 plus 1 is 1. So that's our 0.1. And then for 0.2, we're just plugging in a for t. So take all the t's out and put in a's. Simplify it if you can. Okay, there's nothing to simplify. So for 0.2, it's going to be a squared plus 3a plus 1. Now we're going to find the slope between these 2 points. So our average rate of change is equal to, we're going to do change of y over change of x And when I say this, I'm meaning just the standard, the output over the input. So again, these are, the y is the g of t. So g of t sub 2 minus g of t sub 1. And then the x's are t1 and t2. So, and do it in the same order as the top. So t2 minus t1. Okay, and then that's going to get me, so this expression, a squared plus 3a plus 1 minus t sub 1, which is g of t sub 1, which is 1, all over, and then t sub 2 is a, right? T sub 2 is a, t sub 1 is 0. And then simplify this. So the 1's cancel. A squared plus 3a over a. Now notice all three of these terms have an a in them. So I can factor an a out of the top. So a squared divided by a is a. 3a divided by a is 3. And then that a that I factored out of the top can cancel the a on the bottom. And then I just get a plus 3. So that's my average rate of change. So whatever a is plus 3. Our second learning objective for today is use a graph to determine where a function is increasing, decreasing, or constant. Using a graph to determine where a function is increasing, decreasing, or constant. So if you look at this graph that's given in the book here, here they have this, it's saying it's increasing and they're pointing to this part. Now the idea is we want to standardize what do we mean by increasing and what do we mean by decreasing. So if we had a graph, basically it means it's going up or it's going down. Increasing is going up, decreasing is going down, constant's going, it's not going up or down, it's staying flat. So now the problem is, what do we mean by going up and down? So if you were to watch me graph and I said, hey, look, I'm graphing and it's going down, so that's decreasing. But then tomorrow I graph that same line and I say, hey, well, let's erase that. Hey, that's increasing. So which is it? Is it increasing or is it decreasing? So what we do is we make a standard and we say, well, if we think like we read in English at least, from left to right. So as I move from left to right, is the graph going up or down? So as I move this way, the graph is going up. So that's increasing. So as I move this way, if the graph is going down, then that would be decreasing. I guess I should have drew my, right? So as I go that way, I'm going down, so that's decreasing. So this would be decreasing. And then this would be increasing. So again, just kind of run your pencil on the graph moving from left to right and then just look at the vertical position. Is it going up or is it going down? That would be increasing or decreasing. So we start on the left. You see we're going up, 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 stop. Now we're going down, 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 down. So right here, there's a change. So this portion of the graph, now you just look at the x-axis. This portion of the graph from negative infinity to negative 2, it's increasing. See, now we're going down, 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 stop. Now we're going to turn around, start going up, up, up. So again, here's the next break. So from negative 2 to positive 2, negative 2 to positive 2, it's decreasing. Okay? And then again, up, 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 up. So from 2 to infinity, it's increasing. So the function is increasing on this portion of the graph from negative infinity to negative 2, and also from this portion of the graph from 2 to infinity. Okay, so again, this is the x intervals that the y values are going up as you move from left to right. Okay, and that's kind of what this is saying. So the y values are increasing as b. So b is greater than a. So if b is on the number line, this is a and this is b. So that's from left to right. Okay. So from left to right, that's what this bottom part is. And then these are the y values. So f of b is greater than f of a, right? So if we start at a, we're going from left to right, this is going up. And then this one will be going down. F of b is smaller, right? So if this is f of b is smaller than f of a. So here's f of a. Remember, that's a y value. This would be f of b. So see, that's going down. All right. Hopefully that makes sense. In our next learning objective, use a graph to locate the local maxima and local minima. Okay, so a local maximum is basically if you take an open interval on the x-axis, right, and you want to find is there a point that's bigger or higher or greater than every other y value, right? So if you look at just a portion of this graph from, say, from negative 3 to 1, say, right? See how we're going increasing, 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 stop, and we turn around, decrease, decrease, decrease. So that point where you change from increasing to decreasing, we call that a local maximum. Okay, and it's the y value that's the local maximum, and it occurs at whatever the x value is at that point. Okay, and then local minimum. Oh, and then sometimes you'll see some books we call this relative instead of local. Relative. So we have absolute maximum and relative maximum, and then we have local. The alternate words would be local for relative and global for absolute. And we'll talk about that in a little bit. Okay, so for the local minimum, it's the same thing. Is there a point that if you just look at a portion of the graph where the y value is the lowest, it's lower than all the other y values in that interval? Okay, so if we look at this portion of the graph right here, you can see basically you're looking for humps, peaks, and valleys, right? So right here, right, we're in decreasing, 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 decreasing. Decreasing. We stop. We're not increasing or decreasing anymore. Now we turn around, increase, 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 increase. So that point where we switch from decreasing to increasing is going to be a local minimum. And again, the y value is the local minimum, and then the x value is where it occurs. It occurs at x equals 2. So this graph has a local maximum that occurs at x equals 2. The local maximum is 16. And it has a local minimum at x equals 2. Did I say this was negative 2 here? The local minimum is negative 16, and it occurs when x equals 2. Here's the more formal definition of increasing, decreasing, and then local and minimum, local minimum, and local maximum. All right, so a function f is an increasing function on an open interval. So we're talking about the x values. If f of b, that's a y value, is greater than f of a for any two input values a and b in the given interval where b is greater than a. So remember, this is basically saying we're moving left to right, and then this is saying the y values are going up. So that's kind of the way you interpret this. So that's the actual formal definition. For decreasing, notice it's going to be the same thing, open interval f of b. Now the only difference is greater than, this is less than. So the y values are going down as you move from left to right. Okay, and notice here b is still greater than a because we're still moving left to right. Okay, a function f has a local minimum at x equals b if there exists an interval a to c. So again, those are x values. So b is in that open interval somewhere between a and c, such that for any x in the interval a to c, we're just saying the same thing again, f of x is less than or equal to f of b. Okay, so basically we're saying this is going to be at the lowest point. Otherwise, f of x has a local minimum at x equals b if there exists an interval, or likewise, I'm saying, sorry. Likewise, f of x has a local minimum at x equals b if there exists an interval a, comma c, so that's an open interval, with b it's in between a and c, such that for any x in the interval a to c, f of x is greater than f of b. So all the f of b has to be the smallest value, right? So remember, that's y value. So if you think of it this way, if this is f of b right here, so then this would be b. We have to have an open interval from a to c where all the x values have to be greater than the f of b. So if we have something here, it has to be above, this point has to be above that. So it's basically going to look like that. So all these x values, when you plug it in, f of x is bigger than f of b. F of x is bigger than f of b. Okay? And then you can do the same thing for this one. So this is a local minimum. And then for this one, we just turn that around. F of b is bigger, so that's at the top. F of x is less than. So again, if we have b, so this is b, f of b, and if we have an open interval, a, c, we're saying that if I plug in the x value that's in this interval, that has to be less than f of b. So it has to be below it. So something like that. So this will get us a local max. Okay? And it's not the point. Remember, the local max is equal to the y value, and it occurs at x equals b. Okay? So the x coordinates where it occurs, the y value is the local max or the local min, whichever case we're talking about. Example 7, finding increasing and decreasing intervals on a graph. Given the function p of t in figure 6, identify the intervals in which the function appears to be increasing. So again, if you just put your pen or pencil on the graph furthest to the left, and as you move from left to right, you're going down, 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 down. Right here, we stop. Now it's going to go up, 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 stop. Down, 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 stop. Up, 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 up. So this is increasing from 1 to 3. That's increasing. And then this part's decreasing. So starting here 4 to infinity, that's going up. And see, because the arrowhead, it's going, this will go forever. So this is increasing. So the function p of t is increasing on the intervals, you don't have to write the interval. You can just write interval notation on, let's see, we got to do open intervals by definition. So 1 to 3, even though these are closed dots, in our definition, we defined it to be open intervals. So you always answer with open intervals. Some books, sometimes some books will debate whether you do a closed interval or open interval. This book is using those as open intervals. So regardless if this is a closed dot or not, doesn't matter. By definition, we're doing open intervals. So union, and then from 4 to infinity. And again, same thing, open intervals. Okay, example 8. Find the local extrema from a graph. So graph the function f of x equals 2 over x plus x over 3. Then use the graph to estimate the local extrema of the function to determine the intervals. So I wouldn't expect you to graph this right now. We'd probably cover this later. The 2 over x is from our what is our toolkit of functions, right? The 1 over x is, oops, something like this. 1 over x is this. So 2 over x is going to have a similar shape. It's just going to be a little bit more pronounced there. But anyway, it'll have a similar shape. And then the x over 3 is a line. And then you would add those two graphs together. X over 3 would be something like this. And then you would add these together. But I wouldn't expect you to know right yet how to graph that. So we just go to Desmos. Let me pull that up. Okay, so here's Desmos, desmos.com, graphing calculator. So here's what I was just talking about a minute ago. So if I did 2 over x, it's that reciprocal function, but with a multiple of 2, a scale factor of 2. So it's vertically stretching it. And then this is just a line. And then if you add those together, those two things together, you're going to get this shape here. And notice, if we go back just to kind of notice here, if you notice how this, we have an asymptote, this is going to 0. But then the line, if we take this y value and add it to something almost 0, what happens is it's going to be really close to the green line. So let me get rid of the blue for a minute. So you can see how it's kind of approaching that green line. So we have what we call a slant asymptote because of that. Anyway, don't worry about that too much right now. We'll learn a little bit about that stuff later. And then we are trying to find the local extrema. So basically we're looking for the peaks and valleys. And what's nice about Desmos, right? So you can see that it's right about in this neighborhood, right? If you just click on the graph, it puts it for you. So the local, this would be a maximum, would be negative 1.63, and then the local minimum would be there. Okay, so that's really nice with Desmos. You can just click on it and it'll show you what that local max and min is. So it's kind of a built-in function there. So we have this one is a local minimum, local min at, local min is equal to 1.63. We'll just do 2 decimal places, and occurs at x equals 2.45. And then we have a local maximum is equal to 1.6, negative 1.63, and occurs at x equals, okay, I chopped it off, but that's obviously negative 2.45. Okay? So again, encourage you to use that. Remember, on the tests, you won't be able to use a graphing calculator. So if I give you a question like this with something that I don't expect you to know how to graph quite yet, I'll give you the picture of the graph if I put it on the test. Example 9, finding local maximum and minimum from a graph. So for the function f, whose graph is shown in figure 9, find all local maximum and minimum. So remember, we're looking for the humps, right? Peaks and valleys. So right here, that's the bottom, so that's a local min. And here is a local max. So we got a local minimum is equal to, what's the y value? Remember, the minimum's the y value. So that's negative 2. And it occurs at x equals, what's the x value here? Looks like negative 1. Oh, they got the scale different for the x and y. You got to pay attention to that. Okay, so that would be negative 1 for the x and negative 2 for the y. Remember, the y value is the local max or min. Okay, now the local max, the y value is 2, and that occurs at x equals positive 1. Analyzing the toolkit functions for increasing or decreasing intervals. So you should, again, these are our basic functions that we should get real familiar with. You should know all these. I'm not going to go through all of them again, but basically a constant function, it's not increasing or decreasing, so it's constant everywhere, right? Identity function, strictly, as you move left to right, strictly increasing. I said I wasn't going to go over it, but I'll do a real quick one like this. Quadratic function, it's increasing. So right here, the bottoms are a local minimum, x equals 0 at x equals 0. Okay. And then it increases from 0 to infinity, and it's decreasing from negative infinity to 0. Okay. And for our cubic function, it's strictly increasing. There's no local min or max. Reciprocal, it's strictly decreasing, left to right, decreasing. Reciprocal squared, it's increasing on the left side, negative infinity to 0. It's decreasing on the right side from 0 to infinity. Cube root is strictly increasing. There's a special word for that if it's strictly increasing or strictly decreasing. We call it monotonic. I won't quiz you on that yet. Square root, it's strictly increasing over its domain. And remember, the domain is just the positive numbers, or non-negative, I should say, greater than or equal to 0. And then it is absolute value is increasing on the right side and decreasing on the left side. Okay, so you should be real familiar with these. You're going to see them a lot, especially when we get to the chapter where we learn the transformations. Okay, and on to the last learning objective for today. Use a graph to locate the absolute maximum and absolute minimum. All right, use a graph to locate the absolute maximum and absolute minimum. The absolute maximum of f at x equals c is f of c. So again, it's the y value, where f of c, that y value, is greater than or equal to f of x for all x in the domain. So when we say absolute value, we're looking at the whole function over its entire domain. So you can almost think of it as a ceiling. So if we look at this example, you see how I can put this, and that kind of traps. There's nothing higher anywhere on the domain, on the graph, nothing's higher than this point. So that would be the absolute maximum, that y value there. So this has an absolute, what happened? Let's see if I can do that again. Probably just went to the bottom. Oops. Try that one more time. Okay. And then, so basically that point and that point is where you have the maximum. So we have an absolute, and remember I said if some books, they refer to it as global maximum. So they would use global and relative, or absolute and local. Okay. So absolute max is equal to that y value, and then it happens in two places, and occurs it's getting late, occurs at x equals -2 and x equals 2. Okay, and then now think about the floor, right? So you can see right here's the floor. Here's the floor, and that looks about, there's -8. It looks like halfway, so -10. So that's at -10. So the absolute minimum, oh, I never finished reading the definition. So absolute minimum f at x equals d is f of d. So again, that's the y value, where f of d is less than all other y values, f of x, for all x in the domain. So basically that'd be the floor. That's kind of the way I think of it. So the absolute minimum is -10, and it occurs at x equals, what's the x coordinate here? 3. Right? So that's the way you would do that one for absolute max and minimum. Oh, and by the way, minimum this would be singular, and the ma, right? ma, that's for plural, right? So maxima is plural for maximum. Maximum would be singular. So this one has one absolute maximum that occurs at 2 different spots. Okay, and that is the end of today's lesson. So make sure to practice, practice, practice. Do a whole bunch of exercises. Turn in your work on Canvas, and I will see you next time.